In Chapter 12, we will continue our look at geologic time and how the Earth has changed or evolved over time. Our first topic that we look at is what makes Earth habitable? Why is Earth in the habitable zone? If we look at astronomy, we look at all of the different missions that NASA has flown to research other planets and look at other areas within our galaxy. One of the things that they have defined is this habitable zone. And this is the region around a star or planet where we have sufficient atmospheric pressure that can maintain liquid water on its surface. If you read anything about NASA missions, one of the things they're always looking for is liquid water. Without liquid water, a planet or a star can't be habitable. So Earth is the right planet. What are some of these characteristics? Well, it's the right size. Okay. If Earth were larger, then the force of gravity would be greater. And like the large planets, the atmosphere would be too heavy and it would be filled with things other than, oxygen and nitrogen and ozone. If Earth were smaller, then there wouldn't be enough gravity and we wouldn't be able to maintain the atmosphere as we know it. We've talked about the structure of the Earth in terms of its crust and core. If we didn't have that lithosphere overlying the asthenosphere, then we wouldn't have plate tectonics, and the entire Earth would likely be covered by an ocean. So we would have no land. We would have no terrestrial environments. It would all be oceanic. And then if there was no metallic or molten metallic outer core, most of the life forms on Earth would no longer exist. The reason for this is without that flow of iron in the core, we wouldn't be able to have a magnetic field that surrounds us. And the magnetic field is what prevents the cosmic rays from the sun from basically baking off our atmosphere. We are the right location. We're the right distance from the sun. If we were 10% closer to the sun, our atmosphere would be different. It would retain more greenhouse gases, which would make Earth too hot. If it were 10% farther from the sun, it would be too cold. We wouldn't have a water cycle because the oceans would freeze. The right time. Our atmosphere has developed over time. It was about 2.5 billion years ago that the atmosphere with free oxygen came into existence. And then we got hit by an asteroid about 6 miles in diameter, roughly 66 million years ago. And this wiped out the dinosaurs and made it where mammals could inhabit the Earth. So Earth developed under just right conditions to be able to support higher life forms, and they refer to this as the Goldilocks scenario, where if we looked at the porridge, daddy's porridge was too hot and mama's porridge was too cold and baby's porridge was just right. Well, Venus is too hot, Mars is too cold, and Earth is just right. Now, the next section of your book, section 12.2, talks about birth of the planet and the Big Bang Theory. Now, we're not going to cover this in this class because just like with creationism, Big Bang is a theory. And when you look at your religious beliefs, you either believe in the Big Bang Theory or you believe in creationism. And to avoid having a religious or a philosophical debate, we're not going to discuss either. So we're just going to skip right over 12.2 and 12.3 and pick back up at 12.4, the Precambrian history. So in the Precambrian time period, we have about 90% of Earth's history. It's our first 4 billion years. We have the Archean eon, which means ancient age, and the Proterozoic, which means early life age. And when we look at Precambrian history, I like the analogy that your book used. It says it's written in scattered speculative episodes like a long book with many missing chapters. In the last chapter, we talked about how, we could look at rocks to help give us the story and help explain and look at fossils, and we could use the fossil record, we could use correlation, and these different tools that we could use to determine relative ages or relative dates. But then we looked at the idea of unconformities, where we know that erosion took place. So if we look at the Precambrian time, there's so many missing pieces because of erosion and the lack of fossils. So it's really difficult to determine everything that happened during the Precambrian because there is no record of it at all. What we do know is that a lot of our continental crust was created during the Precambrian. And we're going to watch a smart video that shows us how this crust came to be.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how the first crustal land masses formed early in Earth history. If you look at this map, you'll notice that there is a lot of young rock in the world. And if you go towards the cores of the ancient continents, then you'll notice that there is older rock there. And the older rock surrounds progressively still older rock. So the Archean cratons are shown on the map in pink, and rocks that are older than about 3.5 billion years are shown as the purple dots. Early plate tectonics did not look anything like modern-day plate tectonics. Instead, it probably started off looking something like this. This is the surface of a lava lake in a volcano in Ethiopia. And you can see here that basically fresh lava is welling up in certain places. That's the really light-colored areas. And then there is a sort of primordial crust forming, basically solid rock. That's the black material. There are spreading centers, and there are even little subduction zones where one layer of that crust goes underneath another layer of that crust. So there's sort of primordial convergent and divergent boundaries at work here. Evidence suggests that these earliest scraps of continental crust formed in the way that's illustrated here. You can see basically that we've got a trio of volcanic island arcs being produced at these ancient subduction zones, and there's also an oceanic plateau that's being generated thanks to a mantle plume. Sediments are being shed off of these young land masses and accumulating near the trenches or on their passive margins. And the idea is that then they collide together, and basically because of the thickness of the crust there, they're less likely to subduct. So it's less dense crustal material, and it's thicker, and as a result they tend to glom on together and stick to one another. In addition, partial melting in the lower portion of that crust could form felsic magmas, in other words granites or related rocks that can end up rising up to form plutons or even felsic volcanoes. What would you expect to see if you zoomed in on the sediments that are located in these collisional zones where these ancient land masses have collided? Well, hopefully you would say that you would expect to see some of the signatures of mountain building. So for instance, here in this photo, you can see some of the rocks at Isua in Greenland, and you can see that they have some beautiful folds in them. So these folds are some of the evidence of compressional forces that have gone to work on these rocks. You can also see a metamorphic foliation, which overprints the sedimentary layering in these rocks, and that would also be a consequence of these ancient collisions. So even though these rocks are really profoundly ancient, they actually have many of the same characteristics as do rocks that are forming today, and we can learn about them thanks to the context that rocks today provide.
If we focus in on North America and how it came to be, we actually get a really good example of this kind of piecemeal assembly of the continental crust, or the continental crust into an actual continent. With a few exceptions, very little continental crust older than 3.5 billion years remains. There was a lot of growth that occurred between 2.5 and 3.5 billion years ago, and pretty much by 1 billion years ago, the North American continent was pretty much built. So now we have another smart figure that'll walk through the building of the continental crust of North America.
Hello, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe how North America grew over geologic time. Take a look at this geologic map of North America. Basically, what's being depicted here in the different colors are the different ages of the continental crust. The oldest crust depicted on this map is shown in purple, and then that's surrounded by belts of slightly younger crust, which is shown in red, younger crust still in gray, younger in green, and then orange, and the youngest of all is in yellow. So you can see that there's this sort of pattern where there's a nucleus to the North American continent, and then more material was added on to the edges over time. Let's begin by taking a look at this orange swath right here. This is called the Grenville Province, and the Grenville Province was added on to the North American continent around 1.2 to 1.0 billion years ago. At that time, all the continents were glommed on together into a massive supercontinent known as Rodinia, and so new material was added on to the edge of the North American continent at that time. But that wasn't the end of the story. You can see that then more material was added on outboard of the Grenville Province during a later period of geologic time, and the yellow on this map basically indicates crustal blocks that are less than 1 billion years old. The Appalachian crustal block came about as a result of the assembly of Pangaea. So we can see that basically we went from the post-Rodinia breakup world where the continents were separated towards a new world where first North America and Europe collided, followed by the collision of North America and Africa to produce the supercontinent Pangaea. And the young Appalachian mountain belt ran along that collisional zone right there. So when you look at the Appalachians today, they don't really look like awe-inspiring mountains like the Himalayas or the Alps, but they actually have a fascinating geologic history hidden beneath that mantle of forest. You might ask yourself whether the pattern that we see in the North American continent applies to other continents on Earth as well. Indeed it does. No matter which continent we look at, we see this same pattern of really old crust surrounded by slightly younger crust, surrounded by slightly younger crust, and with even younger stuff added on outboard of that. So basically this is the legacy of collisions of crustal fragments over a long period of geologic time. Thanks for your attention.
So as he mentioned on the last Smart Figure video, this supercontinent called Rodinia. So supercontinents, of course, we've looked at Pangaea before. We've never discussed Rodinia. Supercontinents are large land masses that contain all or nearly all of the existing continents. And Rodinia was the earliest well-documented supercontinent. It formed during the Proterozoic eon, which was about 1.1 billion years ago. Its configuration is a lot different than Pangaea. So here is what we believe from evidence that Rodinia looked like. And it started splitting apart between 800 and 600 million years ago. And by the end of the Precambrian, era, many of them had reassembled, producing Gondwana or Gondwanaland and Laurasia. So if we kind of look at this figure here, Africa was actually at the South Pole. You see there Northern Europe was very close to the South Pole, and North America very close to the equator. But you'll notice that everything was pretty much centered around the North Pole. We didn't have anything in the smaller latitudes up near the North Pole. So if we take a look at these supercontinents of the Precambrian, we have what's called a supercontinent cycle. This involves the change and dispersal of one supercontinent, followed by a long period of time when they are reassembled into a new supercontinent with a different configuration. And what this does is it allows the Earth's continents to evolve and change, but it also affects climate and it causes changes in sea level. So the movement of continents from one supercontinent into individual pieces and back to another supercontinent changes the patterns of ocean currents as well as global winds. Now, ocean currents and winds greatly affect temperature and precipitation. And we'll talk more about why that is when we get to our chapters on weather. So when we have all of this movement and rearranging that's taking place in this supercontinent cycle, we get changes in climate. So this image in your book kind of shows the difference in ocean currents, and we're going to watch another Smart Figure video that's going to walk us through exactly how this happens.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the tectonic cause for Antarctica's glaciation. Continental ice sheets are a rarity in the modern world. If you were to go back in time to the last glacial maximum around 18,000 years ago, you'd see much more of the world covered in ice. However, today we only have ice sheets really in two places on Earth. One is the island of Greenland in the northern hemisphere, and one is the continent of Antarctica in the southern hemisphere. Now, Antarctica is an interesting case because it really was not subject to the sort of on-again, off-again glaciation that characterized the northern hemisphere. Its ice has been flowing for around 30 million years. And the reason for that is all about ocean currents, and the ocean currents basically are determined by the position of the continents. So here in this picture, you can see an image depicting the position of the continents around 50 million years ago, and we can also see the circulation of the ocean at that same time. You can see in two spots here that warm currents are running down the eastern side of continents, down the eastern side of South America and Africa, and they end up basically bringing warmth to Antarctica. And this is very similar to the way that the Gulf Stream, the modern-day warm current that leaves the Gulf of Mexico, the Caribbean, and Florida, and heads up along the east coast of the United States, brings warmth to the UK and to Iceland. But in Antarctica's case, that all went sour when South America broke away from Antarctica, and Africa drifted further away, and a new current developed that basically encircled Antarctica, and that current is called the west wind drift. So the west wind drift basically just had cold water wrapping around Antarctica, and those warm currents were still coming down from the equator along the coast of South America, for instance, but now that current hit the west wind drift rather than hitting Antarctica. So once this situation got established, Antarctica began to build up massive ice sheets, and they've been there for tens of millions of years. Thanks very much for your attention. This has been another Smart Figure.
So there you could see how ocean currents can affect climate. Something else that can affect climate is the creation of large mountain systems that are created by the collision of these large cratons. One example is when India slammed into Asia to create the Himalayas. Mountains, of course, much higher elevations, and so they have lower average temperatures and have precipitation. But as air rises over the mountains, the region that is downwind from it is relatively dry, and we can kind of see this with the Gobi Desert, which lies on the northern side of the Himalayas. Okay, also looking at the Sierra Nevada mountain range in the United States, and then the Great Basin Desert that lies directly to the east. So mountain ranges can affect climate as well. Now, if we look at sea level changes, if sea level rises, then shallow seas start to advance up onto the continents. We can find evidence of this in the fossil record because of the marine sedimentary rocks that we see along modern land masses, including about the eastern 2/3 of the United States. When we come in the lab this week, I'll show you some of the fossils that have been collected in southern Arkansas that let us know that it was once covered by ocean. There are a lot of marine organisms that we can find fossils of around here. The other thing that happens with sea level changes is seafloor spreading. When the rate of spreading is rapid, as we see it today along the East Pacific Rise, the production of warm oceanic crust is high. It's warm because it's close to the molten magma that's underneath it. And the warm oceanic crust is less dense than the cold crust that's already there, that's already present. So fast spreading ridges occupy more volume in the ocean basins. So when rates of seafloor spreading are high, the new crust takes up more volume, which makes the sea level rise. And this is what causes the shallow areas to be overrun with water. So if we now move to the Phanerozoic, which is the time span since the close of the Precambrian, this encompasses 541 million years. Phanerozoic means visible life, and it's divided into 3 eras: Paleozoic, ancient life; Mesozoic, middle life; and Cenozoic, recent life. And the Cenozoic is where we are now. So we're going to take a brief look at some events that happen during each of these. So if we look at the Paleozoic, we get the formation of Pangaea. So we had Rodinia, the supercontinent, it broke up. Then we got Pangaea, okay, our second supercontinent. This was, the collisions that occurred between Laurasia and Gondwana to eventually form Pangaea in the late Paleozoic. It took about 300 million years for that to happen and form several mountain belts, as you can see here. It reached its maximum size between 300 and 250 million years ago. If we look at the Mesozoic history, the Mesozoic era is about 186 million years, and it's divided into the Triassic, Jurassic, and Cretaceous periods. So looking at some of the things that happened in the Mesozoic era, we have the breakup of Pangaea and the evolution of modern ocean basins. So it began with most of the world's continents above sea level. And we can see this in some exposed sedimentary rock. And when we look at this rock, we know that it is terrestrial and not marine. As we moved into the Jurassic period, the sea started to invade western North America, and we got continental sediments that were deposited on what is now the Colorado Plateau. There was an enormous desert that occupied most of the American Southwest during the Jurassic period. And something else that we can find associated with these deposits is the Morrison Formation. And the Morrison Formation is one of the richest dinosaur fossil areas or layers that we've found. We also had coal formation in western North America. And this occurred as we moved from the Jurassic period into the Cretaceous. The sea level rose again, and along western North America, as well as into the Atlantic and Gulf Coast areas that created these coal swamps. And in these coal swamps, we had these very rich, humid, high precipitation, warm weather, because we were situated a little bit closer to the equator. And so we got these massive coal deposits. The Crow Native American Reservation in Montana has nearly 20 billion tons of Cretaceous age coal. And this is very high quality coal because of the climate that was occurring at the time. And then we have the breakup of Pangaea. We got the split between North America and Africa, and this led to the creation of the Atlantic Ocean. And then this resulted in crustal deformation along the entire western margin of North America, and subduction occurred as the North American plate and the Pacific plate were interacting with one another. It led to some batholith formation in Idaho, granitic plutons in the Sierra Nevada, and we got the North American Cordillera that extends from Wyoming to Alaska. That makes up the Sierra Nevada, the Rocky Mountains, and the Bighorns, the Sangre de Cristo Mountains, all of these mountains out west. Now moving into the Cenozoic, we go back to where most of North America was above sea level again, so our sea level started to drop again. This is the past 66 million years. Physical landscapes and life forms that make up our modern history started to come into existence. The continental margin of eastern North America was pretty stable. We get a lot of marine sedimentation, and so we get a lot of deposits of marine organisms around that area. And out west, the Laramide orogeny that began in the Mesozoic era continues and then ends as we go into the Cenozoic era. We got the development of the fault block mountain range and the formation of the basin and range province that we looked at in the last chapter and the chapter before. We got the elevation of the western interior, and this led to more rivers being formed, which led to the canyon formation that we see with the Grand Canyon, the Black Canyon of the Gunnison River, and the Grand Canyon of the Snake River as well. We also had a lot more volcanic activity. We have the formation of what's called the Columbia Plateau, which is basically a fluid basaltic lava flow that covered 3.4 million square kilometers out west. Now the next section talks a little bit about the origin of life, and just like before when I mentioned that we're not going to get into Big Bang Theory versus creationism, kind of the same thing here. So we're going to skip through this section on Earth's first life and pick back up with the Paleozoic era. So the Paleozoic era is where we really started to see really an explosion of life. This is called the Cambrian explosion. It lasted 20 to 30 million years, and this is where we start to see all of our major invertebrates becoming widespread. Life was pretty much restricted to oceans. All of these organisms needed water to survive, and so we didn't really have any land organisms at this time. The Cambrian was the golden age of the trilobites. Then, as we moved into the Ordovician period, we see the cephalopods, which are the ancestors of modern day squid and octopus. We got a lot of diversification because we started to see the emergence of predatory lifestyles. We also started to see the development of hard shells and skeletons, and this is where we really start to bump up the fossil record, because the hard shells, the skeletons, they last longer. They're not destroyed like soft tissues are. So this is where we start to really get our extensive fossil record. As we moved into the mid-Paleozoic, we started to get land plants, and then forests. We started to get vertebrates, those organisms with a backbone. We had placoderms, which were the ancestors of the modern fish that we see. We started to get more fish that were evolving, the sharks with their cartilage skeletons and the bony fishes with their skeletons made of bone. We had these lobe-finned fish that started to live on land, which gave way to amphibians. And amphibian means both ways of life. Amphibians are tied to the water. They have to have water to lay their eggs. And so then we get reptiles. Reptiles can live strictly on land. They're not tied to water. So reptiles began to take over the terrestrial environment because they were the first group that really had all of the necessary adaptations to be able to do that with the development of the amniotic egg. Amphibians have to lay their eggs in water, but reptiles have eggs that have a hard shell, so they can be laid on land. So now we'll watch another smart figure video. This comes from page 395 that really kind of takes us through the development of these organisms through the Paleozoic, the Mesozoic, and even into the Cenozoic era. So we'll take a look at this, and I'll interject a few things as we're going through.
Hi there, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe the sequence of branching events that have resulted in the evolution of tetrapod animals. Now, the word tetrapod basically just means 4 legs or 4 feet. And all tetrapods are vertebrate animals. So basically most of the animals that you're familiar with are going to be tetrapods if they have a backbone. The exception to that would be fish. Fish have backbones, but they don't have 4 limbs. But all tetrapods are derived from lobe-finned fishes. So lobe-finned fishes are the probable ancestor of the very first amphibians. From the amphibians came the reptiles, and from the reptiles came the mammals and the birds. So let's go ahead and take a look at this first transition here, from the lobe-finned fish to the earliest amphibians. If you go and you look at the skeletal anatomy of lobe-finned fishes and early amphibian fossils, you'll find that they are very similar. And one of the things that they have in common is a common structure to the forelimb. So you'll see here the radius is present in both organisms, the ulna is present in both organisms, and the humerus is present in both organisms. And then there are also some sort of finger bones out towards the distal tip of that limb. There were other adaptations that the earliest amphibians had to develop, such as lungs, so that they could move around out of water, that lobe-finned fishes never got. Those amphibians that still survive today are basically a link back to that earliest divergence of tetrapods from fish. All right, and then we've got the reptiles. The reptile line is a big and bold one. All right, that's right in here. Let's go ahead and take a look at a couple of reptiles. This is the skeleton of a dinosaur, so a fossilized dinosaur found in the ground. Dinosaurs, of course, are very charismatic and well-known reptiles. Less well-known are the ichthyosaurs. These were marine reptiles. This is still a tetrapod, though. Notice that it's got 2 forelimbs and then there are 2 hind limbs as well. So even though this organism returned to the water, it still counts as a tetrapod. Later on, in the mammal lineage, whales would do the same thing. So whales count as tetrapods too, even though they don't have 4 legs in the sense of, like a cheetah or something like that. Okay, let me ask you a question now that we've talked a little bit about the reptiles. According to this diagram, are birds or mammals most likely derived from dinosaurs? Well, you can see here that the bird lineage is the one that sprouts off the reptile lineage right there in the neighborhood of dinosaurs during the Jurassic period of geologic time. We actually have really good fossil evidence of this. This is an organism that, when it was first discovered, was thought to be a dinosaur, but then they noticed that it had wings. And you can see the feathers here on the wing in the fossil. This is Archaeopteryx. Archaeopteryx had a mix of reptilian features such as teeth and a long tail, and it had some bird features as well, such as wings and feathers. Mammals.
So a little bit more about Archaeopteryx. So this came about 160 million years ago. They believe that there were more feathered dinosaurs, but Archaeopteryx was one that we really had awesome fossil evidence for. The dinosaurs flourished for nearly 160 million years, but there was a mass extinction that occurred. The researchers believe that this was kind of a 2-step process that led to this mass extinction. During the last few million years of the Mesozoic era, average temperature on land increased by more than 20 degrees Celsius, which is about 40 degrees Fahrenheit. And we also got a lot of volcanic eruptions that were happening at the same time. This released carbon dioxide, which led to the greenhouse effect and that warming temperature. And then about 66 million years ago, Earth was hit by that large 6-mile-wide asteroid that hit in the southern portion of North America, which is now Mexico's Yucatan Peninsula, so right there in the Gulf of Mexico. So what happened there was dust reduced the amount of sunlight, which resulted in cooling, which resulted in less photosynthesis by the plants, which meant that the herbivores started to die out, which then meant that the carnivores started to die out. We do have some evidence of this. There is a thin layer of sediment, less than a centimeter thick, so very, very tiny layer of sediment that contains iridium, which is really found in outer space and not so much on Earth.
On the other hand, did not come off of the dinosaurs. You can see that the mammals split from the reptiles in the late Paleozoic. And there were several lineages of mammals that went extinct, but there were other ones that went on to diversify. In particular, when the dinosaurs went kaput, that was a time that mammals really diversified. And so you see their numbers and diversity increase. That, of course, includes both modern-day mammals, but also ones that are extinct, including the recently extinct woolly mammoth.
So the woolly mammoth is not the only extinct animal that we have. We had mastodons that went extinct, saber-toothed cats, giant beavers, the large ground sloths. Don't really exactly understand what caused the extinction of these animals, but could be that early humans hunted them to extinction because they were so large, they were easy to shoot and kill, and so this could have led to their demise. So that brings us to the end of chapter 12.